So in our last session, we had a discussion on the overcurrent protection, non-directional overcurrent protection. And in our today's session, we will discuss on directional overcurrent protection, followed by differential protection. And if time permits, let's have a look on the distance protection also. Three types of protection. So by this today, mostly we will complete the protection chapter, except the settings protection coordination will be left. That will be covered in our next classes. The ETAP, dialects, and these sessions will be covered in the next classes. So let's start the concept of directional protection team. So let me share my screen to you. Team, are you able to see my screen? Fine. So let's see. So here, so let's assume I am having the source and we are having a breaker here and also a breaker and a breaker. So it is connecting to the load. So if it's connecting to the load, now if the load is here, so whenever the fault occurs, the fault is feeding through this. So if I see the fault current is some 400 amps, so I am making a setting that when a fault current is 400 amps, this breaker has to trip for at 100 milliseconds, suppose, and at 400 same magnitude of the current, this breaker has to trip for some 200 milliseconds and this breaker at some 300 milliseconds. So this is the grading I am providing for all these breakers. Because why this is applicable? Because all the breakers are seeing the fault in the single direction, because the source at only at one end. Because the source is at one end. If the same thing, assume that the source is on the opposite side, other side. Now, the fault feeding for this breaker, suppose a fault occurred here, the fault feeding would be this direction as well as from this direction. Right? Suppose a breaker here, suppose not breaker. Fault is in this direction. Now, for this fault, this breaker is also acting and this breaker is also will act for this fault also. But my intention is I have to operate only this breaker and also only this breaker. Sorry, only this breaker. If any this load is going through this, only this breaker and this breaker has to be operated. So remaining everything will be input. So how to make that? In a clear example, let's see this. I am having a voltage source here. There are two lines. And this is the load. This is the load. Fine. Now, I am having 4 breakers. And this is the breaker here. This is simply resembling to our 220 kV line team. In our 220 kV, 2 lines are going and connecting to the grid, the same application. Now let's see, if a fault occurred in this line, if the distance protection is offered, then it's a separate thing. Now we are talking about the directional overcurrent relay. Suppose if the distance protection is not worked, we will cover the distance protection in the next few minutes. So If a fault occurred here, then the fault feeding will be like this. And also the fault feeding will be in this direction. So the A relay and this is the B relay. Let's assume this is the C and the D. When a fault occurred here, I have to operate only A and B. C and D should not be operated because I went for two lines because of the reliability. If one of the line is failed, other would be there. So I should only trip this section of the line and this section of the line to be in service. So at the same time, in the same philosophy, if a fault occurred here, then the fault feeding from this is this, and other direction is this. So in these two cases, in this case, in the blue one, the C and D breakers to be operated, and in the pink color fault, the A and B to be operated. So how can I achieve with the normal non-directional overcurrent relay? Cannot be achieved. So I have to say that whenever a fault lies in this direction, then you have to operate. Then I am saying the breaker B to be operated. Fine. So 67 is the directional overcurrent protection I am placing here. This will be operated only if the fault lies in this zone. If only fault lies in this direction, then the B will operate. And coming to the C, here also in the C also I am placing the directional overcurrent relay. This also will operate if a fault lies in this direction, both. And if you now you can ask me, so now here in the A also if we place 60 and this direction, suppose let's assume, then this breaker will operate if a fault in this direction. And suppose, and for this, suppose if you are placing the directional overcurrent relay in this direction, 67. Now, in some cases, if it is a two phases, no problem. If it is a single phase, if it is a two sources, if a fault occurred here, this breakers will not accurately pick up. Means will not pick up because of the directional or current feature. So what generally we will do is, we will place always a directional feature on paralleling side at the load end, and this side general overcurrent protection will be enabled. So it is seeing the fault on both directions, as a kind of a backup for the distance as well as for this. So always, if you want to protect the system on a single direction at some direction, then you have to use the directional overcurrent relay. This directional overcurrent relay will be used if you are having a parallel feeders, or if you are having a generator side on the line sides. If you need, if you find a directional feature is required here to be operated under the directional, so you require in those cases generally we require this directional feature. So this directional relay, how it differs from the non-directional. In the non-directional, we required only the current parameter. In the directional overcurrent relay, we required the voltage parameter with respect to the current parameter to check the directionality. Why I am choosing the voltage is to check the direction of the fault, which direction it has to operate. In a case, generally, always suppose, let's assume this is the V reference, means the voltage reference, polarizing voltage, means the voltage which I am taking for the reference with respect to the current. Generally, the flux developed by this voltage is lag due to this. This is the voltage you are applying to the relay coil team. This is the voltage you are applying to the relay coil. So relay coil, again, it is having some inductance. So the flux generation and the flux of the voltage, the flux developed by the voltage is lagging this V reference with some angle of minus phi. Right? And now let's assume the current, which is maybe a fault current, with a angle of phi, which is in the same line, is leading the V reference. This is the flux developed by this current, flux current. This is the flux voltage. And this is leading the V reference by some angle of theta. Why I considered the current as a leading to the reference, I will explain you in the next 2 minutes. So if this is the way of the current relating to the V reference, this which are applying to the voltage relay, then we in the electromechanical relays, it has to operate it with some torque. So that maximum torque equation we have to found. So torque obviously is directly proportional to the fluxes generated by this the voltage and the current, and the angle between them. We already know this. What is the angle? C sine of theta plus minus phi. So C theta minus phi. This is the angle developed by these two fluxes. And generally, if it is to be maximum, if the maximum torque line where you can find the maximum sensitivity, means good sensitivity, then this maximum torque, it should be the sine of theta minus phi equal to 90 degrees. 90 degrees. So then the theta, the angle of theta is equal to 90 plus phi. 90 plus phi. And so theta is equal to 90 plus phi. So now I am taking a maximum torque angle, which is the maximum torque line, which would be, this is the maximum torque line, which at angle of some tau from this V reference, where I can see 90. See, now let's see in this way. So we derived the theta equal to 90 plus 5, right? Now, if what is the maximum? 90 degrees to my this. So when I receive this 90 degrees to my flux, then the theta equal to 90 plus 5. In the sense, theta minus 90 equal to 5. This is the case. Tau equal to 90 plus 5. This is the maximum torque angle I get. This is the maximum torque angle I get when the tau, when this 90 plus 5, that theta equal to 90 plus 5, then I will get the maximum torque. So that is this. This is the maximum torque angle, which is the line which is passing through that is a maximum torque line. So again, if I implement the same here, comes to here, V reference to the I reference, sine of theta minus, what is the phi? 90, tau minus 90, so tau plus 90. So some theta plus 90 obviously is a cos of theta minus tau. When the cos should be, value will be positive. The cos, because when the torque will be positive, then the relay will operate. So when it will be positive, so it depends upon the cos theta minus tau. So the theta minus tau should be lies between the minus 90 degrees to 90 degrees. So minus 90 plus tau and theta 90 plus tau. The tau 90 plus 2 this. So obviously it is this. And 90 tau minus 90 tau plus 90. So it is give this. So this will use the zero torque line. So this is the zone of operation of my directional overcurrent relay. This is the zone of operation of my directional overcurrent relay. Again, we have to mention the minimum current. What is the threshold current? And also the what is the minimum voltage to avoid the some condition to avoid the failures of the fuses or MCB trips. This may again leads to the chances of mal-operation of my directional overcurrent relay. So to avoid this, generally we will include that angle that also. So now you can see, team, we have to know some important things when you are do the relay settings for this directional overcurrent relay, or when you are trying to establish the relay settings, or when you are doing the testing and commissioning stages. The main important thing is, one is we have to know maximum torque angle, and other angle which is RCA, which is the relay characteristic angle. These are the two angles which you can these are the two angles we will know when we are talking about the directional overcurrent relays. One is the maximum torque angle, other one is the relay characteristic angle. So what is the maximum torque angle? What is the relay characteristic angle? So the maximum torque angle is the angle made by the fault current with reference voltage. Fault current with reference voltage. This is the maximum torque angle, tau. And the relay characteristic angle. The relay characteristic angle is angle by which the reference, the voltage reference can be adjusted to make my relay works with maximum sensitivity. That is my relay characteristic angle. Generally, the relay characteristic angle is it will ranges from minus 95 degrees to 95 degrees. And come to the maximum torque angle. The maximum torque angles before for electromechanical relays, we will consider minus 30 degrees for overhead lines and minus 45 degrees for underground cables. That is some thumb rule. But in the numerical relays, we are not having the setting for this maximum torque angle. So we left with only the RCA, which is the relay characteristic angle. Suppose, let's see now the relay characteristic angle. Suppose, let's assume a fault occurred, and the fault angle is minus 30 degrees, 30 degrees angle, 30 degrees, minus 30 degrees. So it seems that the fault current lags the voltage by reference voltage by 30 degrees. So it's nothing but a maximum torque angle. The fault current lags the voltage by 30 degrees is nothing but a maximum torque angle. Now the relay characteristic angle is 90. See, relay characteristic angle 90 degrees minus 30 degrees will gives you the 60 degrees. This is the characteristic angle. In our before diagram, I shown you that V reference is the voltage that is applying to the relay, and this is the current that is applying to this, and we are having one more line. This is a maximum torque line, right? So I mean that when this is the phase angle between this, so this is the direction. And I said to you that there is some difference between this, some 90 degrees, theta plus 90, right? So 90 minus this, it would be 60. The characteristic angle and a maximum torque angle. So this is the case. Generally, we will assume we will generally consider when we are developing the directional overcurrent relays. And apart from this, we will also have to include the minimum voltage setting, like for fuse failure and MCB trips. Any doubts, team? Till now? Hello? Clear? Team, yes, no, please. Yeah, please. Azim. So today, less population. So I'm allowing you to speak. So you can speak. You can talk. If you have doubts, you can turn on your mic and you can please speak. Azim, please. Previous graph. You mean the vector drawing? Okay, let's draw this. This is the V reference, and this is the flux developed by the voltage, and this is the angle, and this is the angle of I, and the flux is also in line with this current, and this is the theta, and this is the relay characteristic angle. So the maximum torque line, this is the maximum torque line, which is 90 degrees plus theta. So it would be tau. So the maximum torque line would be theta minus this here. Yeah. So, and we are having a zero torque line. This is the zero torque line. And this is the operation of my run. And again, this is the current. Suppose if we make, this is the minimum current. So this is the restraint for this. So above this, the relay will operate. Now, yeah, now you can ask the question. So what is the question here? This is the relay operating zone, and this is the non-operation zone. This is the non-operating zone. In this, suppose if this vector, this I is falling here, the relay will not operate. If this vector is in this from the zero torque line to this torque line, if it is moving in this direction, the relay will operate, and again subject to the minimal threshold value, like pickup current. So this is the pickup current, and again with respect to the relay characteristic angle, we developed the zone of protection. And this is the non-operating zone. This would be the operating zone. Clear? Something else? Oh, fine. And now, team, I told you that why I considered I with reference to the leading to with reference to I. See, the current here, why we considered the current of IF leading to VF is by considering the concept of dead zone, team. Dead zone. Why is, suppose team, if I, let's assume, if I have phase to line to ground fault occurred on my R phase, in R phase a fault occurred, if this fault is near to the PT, so the voltage will collapse, team. You cannot get the exact voltage, means voltage to measure. So the VR will be collapsed. So you are not able to detect, you are not able to do the operation of this directional overcurrent relay because of the voltage collapse. And if it is moving more close to the PT, if the fault occurred near to the potential transformer, the voltage will collapse. So the directional overcurrent relay will not detect because of no voltage signal. So that is the reason what generally it was recommended is, now the V reference is the polarizing voltage I explained, right? So this is the voltage generally we will consider. Suppose if a R phase fault occurred, we will take the R phase current and we are comparing with the Y and B phase voltage. This Y and B phase voltage will not be collapsed. So this voltage we are taking as a reference to develop this. So now again one question that, if suppose a three-phase to fault occurred, then what would be happen? If all the phases will fault happened, all the voltages will collapse. In that case, our numerical relays will take the reference voltages from its pre-fault memory team. Inside its before it has seen the voltage, right? From it, it will take and it will do the action from the pre-fault memory. So this is about the directional overcurrent protection team. And again, in the directional overcurrent protection, one more important point is, this is the case generally for the phase faults. Then what about the directional overcurrent relay, directional earth fault relay, 67N. Now we talked about the 67. What about the 67N? And also, what is a non-directional overcurrent relay, 51N? We have seen the settings, but in the earth fault, we are having two methods always. One is the measured earthing system. Other one is the direct or derived earthing system. In the derived earthing system, we will take the reading of the means we will do the KCL rule, that if all the currents is equal to sum of the currents is equal to 0, then it would be fine. Otherwise, it's a earth fault. In the measured case, what we will do, we will place CBCT, core balance CTs, if it is a low resistance grounding system, and residual ground current, by taking the this is the phases, 3 phases we are having. And this is the neutral connection. From this, these are the relays. This is the other way of one doing. So 3 phases I'm checking, and in the neutral it is following or not I'm checking. So this is the measured type of earthing system. In the both cases it will be there. In the measured case of earthing system, the directional overcurrent relay is simple as we done before. Like taking the consideration of the V reference, I reference, we will do. But in case of the derived, what to be done? In the case of derived, we will consider this polarizing axis, means comparing the other phase of voltages to the other healthy phase of voltages to the affected phase of the current. Here we are considering the zero phase sequence polarization, zero phase sequence current and zero phase sequence voltage will be considered. Otherwise is negative phase sequence voltage or negative phase sequence current will be considered. Again, it depends upon the PT stream. If it is a 5-limb PT, means open delta connection is there, then they will go for a zero phase sequence sequence operation. And if it is a 3-limb PT, then negative sequence operation will be the solution for this. And in earth fault, we already know if all the phases are shorted, there will be a flow of current in the neutral. If the neutral CT detecting a current more than its threshold, it will operate. Simple. So this is about the directional overcurrent relay and fault list. So now let's go to the next one, which is a transformer protections. And the settings of the directional protection will be shown in the next classes, protection coordination chapter. So the transformer thing. See, generally the faults in the transformer, binding faults, could be a core faults, or maybe a tank faults. So such type of faults will be there in the transformer. Binding and terminal faults, core faults, tank faults, or maybe due to the mal operation of OLDCs. Generally, the most occurrence fault is the binding and terminal faults. This will be controlled by the source impedances or by including the neutral grounding resistors. We can mitigate this. And coming to the external, maybe due to the external faults, means outside of the transformer, overload, system faults, or voltages when the frequency drops, these also will affect on the transformer. So to protect the transformer well, because it is a very costlier equipment and the main equipment in the system, we are having much protections in the transformer thing. We are having a much protections in the transformer. Suppose like we are having differential protection is one, which we will call as 87. REF protection 64.